So in this question we're being asked to consider a reaction where a chemical called A is changing into two chemicals called B and C, and we've got the equilibrium symbol there, meaning that B and C can then change back into A. You're being asked to describe what happens to the concentration of A as the forwards reaction starts to occur. So that'll be when you start the reaction. Well, A is changing into B and C, so clearly the amount of A is going to go down, so the concentration will increase. Then part two, the concentrations, what will happen to the concentrations of B and C as the forward reaction begins to occur? Well, at the start there was no B and C, and then as the forward reaction starts to happen, A changes into B and C, which means the concentrations of those two will increase. So looking at the same chemical reaction with A changing into B and C and then B and C changing back into A, we're being asked to describe what happens to the rate of the backwards reaction as more B and C are present. Well, as soon as we start making some B and C, they will start to break back down again to A. And so at the beginning the rate of the backwards reaction is 0, and then as time goes by, as more and more B and C are made, the rate of reaction backwards, that's from B and C back into A, that will increase. Then what will happen to the rate of the forwards reaction as more A is used up? Well, if there's less A around, it's clear that the rate of that will decrease. Now that is shown you on the graph on this page, where you can see the green line is the rate of the forwards reaction that starts high and then gradually drops. And then the rate of the backwards reaction is shown you with the purple line. So the rate of that one starts at 0 and then goes up and then flattens off to the same rate as the other one. So in the filling in of the gaps, you've got eventually the rate that eventually the reaction reaches equilibrium. At this point, the rates of the forward and backwards reactions are equal, or you could write the same. And the concentrations of the reactants and products, now this is important, they no longer change. Now, a mistake that some people make in their exam is that they write the same thing for the rate and for the concentration. So they'll say at equilibrium the rates are equal and the concentrations are equal. And that second one is wrong. The concentrations will get to a certain level and then they will stay there. So we're not saying the concentration of A, B and C are the same. They will all be different, but once we're at equilibrium, the concentrations of those three will no longer change. Now there are two things that can affect the equilibrium position. That's where a reaction settles down, and one of those is pressure, the other is temperature. And you've got to understand these two ideas here, the idea of pressure changing the equilibrium and temperature. Now of the two, pressure is the easier one to understand. Now from your physics you should remember that pressure was to do with the force on the sides of a container as the molecules of a gas hit the sides. So they hit the sides, they're travelling along, they then bounce off the sides of the container and they exert a force on the sides of the container. Now it's best to understand this idea of pressure and equilibrium by using a example. So here we have the example of nitrogen, that's N2, reacting with hydrogen, that's H2, and producing a gas called ammonia. And ammonia has got the formula NH3. Now you are going to have to know those three formulae. In the equation, you've got N2, that stands for 1 molecule of nitrogen, gets added to 3H2, that stands for 3 molecules of hydrogen. Then we've got the reversible symbol, so we're changing into 2 molecules of ammonia, that's 2NH3. Then, as we know, as soon as some of the nitrogen and hydrogen has changed into the ammonia will start to change back into nitrogen and hydrogen. Now, in our modern world, we quite often want to use fertilizers to make plants grow better, and ammonia is a really good chemical to start making fertilizers out of. It contains nitrogen, and nitrogen is needed by plants. So chemists will want to have a way of making ammonia so they can then make fertilizer, and as far as the business is concerned, they are making some money. So they will want to make the most ammonia possible, and so they will be very, very interested in how to make this reaction give them the most ammonia and make it so that the ammonia doesn't change back into the nitrogen and hydrogen during the reaction. Okay, if we look carefully at the reaction, we have 1 molecule of nitrogen and 3 molecules of hydrogen. That's 4 molecules altogether on the left, and on the right we have 2NH3, which is 2 molecules of ammonia. So we have 4 molecules changing into 2 molecules. Now 4 molecules, of course, will take up more space than 2 molecules. In fact, they'll take up twice as much space. So if you increase the pressure, that means you're squeezing your gases into a smaller volume. And so your 4 molecules will want to change into the 2 molecules, which takes up less space. Which means that increasing your pressure favours the forward reaction. You've got to be able to think that through, but you will be given the equation. So you can just say, right, how many molecules, how many molecules? If I go from lots of molecules to small molecules, that will be favoured by the increasing pressure. Now the opposite is also true. If I decrease the pressure, then the 2 molecules will change into the 4 molecules. That takes up more space. They've got more space now because you've decreased the pressure. So if you're the chemist trying to make lots of ammonia, you will increase the pressure because that gives you more ammonia. Now we consider the effect of temperature on the equilibrium, and this one is much more difficult and really takes time to get your head around it. Now reversible reactions will be exothermic one way and they will be endothermic the other way. And in an exam question, you will be told that. So in the example I've given you here of the nitrogen, the hydrogen and the ammonia, you'll be told that the reaction is exothermic forward and it will be endothermic backwards. Now you've got to make sure you've got those two terms in your head. So exothermic reactions, they're the ones that if you put a thermometer into the reaction, the exothermic reaction will make the temperature go up. And that is because the energy is being transferred from the chemicals to the environment. And so the environment gets warmer. That's shown up by your thermometer. The backwards reaction, that's from ammonia back into nitrogen and hydrogen, that is endothermic. Now that reaction takes heat in from the surroundings. So heat is transferred, energy is transferred from the environment to the chemicals. And so if you put your thermometer in that one, the thermometer will show a drop in temperature because energy has been transferred from the environment to the chemicals. So temperature goes down. Now the way I always remembered this when I was doing chemistry as a lad was that if a reaction is taking in heat from the environment, if you were to increase the temperature, in other words, if you were to heat it up, that would actually encourage that reaction. Because the reaction is saying, I want to take heat in from the environment. You give it extra heat, therefore it's going to have the heat there to take in and do that reaction. So the endothermic reaction is favoured by higher temperatures. Now you could work it out like that in your exam, or you could just try and remember higher temperatures favour the reaction that is endothermic. Then the opposite is true. Lower temperatures favour the direction of the reaction that is exothermic. So on the previous slide, the question gave you the information that the reaction one way was exothermic, the reaction the other way was endothermic. But the examiner might not give you that information explicitly like that. They may give you it in an alternative form, as is shown on this slide here. Now here we've put the same equation, so nitrogen plus hydrogen changing into ammonia with the reversible sign in between. And you're then given the information, a triangle, then an H, and then minus 38.5, and then a kJ. Now, what does all of that mean? Well, in science and in maths, a triangle like that is the Greek letter D, which is a delta, and it's used in maths and science to mean the change in something. Now for this one here, we can call the H, we can say that stands for heat. So we're saying that when this reaction happens, the forward reaction happens, we get a change of heat of minus 38.5 kilojoules. Now that means that 38.5 kilojoules of energy have been lost from the chemicals and transferred to the environment. That's why you've got a minus sign there. So if energy has been transferred from the chemicals to the environment, that must be exothermic. So it tells you the reaction that way is exothermic, which means the reaction the other way is endothermic. But you might have to work that out. Now, the second example there shows you one kind of nitrogen oxide changing into another kind of nitrogen oxide. And you're told this time that the change in the heat is plus 58 kilojoules. So in this situation, that tells you that the chemicals have gained 58 kilojoules from the environment, and that's why we've got the plus sign on there. So that tells us that the forward reaction this time is going to be endothermic, and the backwards reaction is going to be exothermic. And then we can apply the principles that we've already learnt. Now you'll notice on this one that you've also got, after the 58 kilojoules, you've got then a per and then MOL. Now that stands for the word mole, which is MOLE, which, if you haven't come across it before, is a large number of atoms or molecules. In fact, it's 6 times 10 to the power of 23, and it's a standard number that's used in chemistry for an amount of substance. So you'll be learning more about that in your chemistry topic 3. So this is exactly the sort of question you might get at GCSE, and this would be aimed at the people getting highest grades. We've got here a reaction. We've got N2O4, that would be nitrogen oxide, in equilibrium with 2 NO2, which is another nitrogen oxide. From the reaction, we can see that we've got one molecule of N2O4 changing into 2 molecules of NO2. So you'd be straight away thinking to yourself, okay, I've got one molecule changing into 2 molecules, so that tells me that if I increase the pressure, that's going to favour the backwards reaction, because I've got the 2 molecules changing into 1 molecule. So increasing pressure will be doing that. And then I've got over to the other side, I've got the delta H, the triangle H, equals plus 58 kilojoules per mole. Now that tells me that a certain amount of N2O4, which is called a mole, you'll learn about that later, that takes in 58 kilojoules of energy to go into 2NO2. So it tells you that the forwards reaction is endothermic. So when you look at the questions now, okay, what's the effect of increasing the pressure? Well, increasing the pressure will increase the backwards reaction with the 2 molecules changing into 1 molecule. Now the likelihood is that you would have to, in this question, tell the examiner what the effect will be and why. So the effect will be the backwards reaction will be favoured. Why? Because the 2 molecules are changing into 1 molecule, and the 1 molecule takes up half as much space as the 2 molecules. Now you've been asked at the beginning, describe the effect of the position of the equilibrium. And here we use a phrase, we say the position, the equilibrium position is shifted one way or the other. So if the backwards reaction is favoured, then the equilibrium shifts to the left. Now increasing the temperature, we know that increasing the temperature favours the endothermic reaction. As we said before, the endothermic reaction is the forwards reaction. So the forward reaction is favoured, and therefore the equilibrium will shift to the right. And finally, what would be the effect of removing some of the NO2? Well, if we do that, then more N2O4 will change into NO2 to counteract that change. The forward reaction is favoured, and so your equilibrium will shift towards the right. And if we have a second example of 2SO2, so that would be sulfur dioxide, reacting with O2, that's oxygen, to give us 2 molecules of SO3, which would be another form of sulfur oxide. Okay, so first of all you have a look, you say, right, how many molecules have I got on the left? Well, I've got 2 SO2 and 1 O2. There's an imaginary 1 in front of the O2. So that gives us a total of 3 molecules. On the right hand side, you've got 2 SO3. So that's 2 molecules. So I've got 3 molecules changing into 2 molecules, and you think to yourself, okay, increase the pressure, that will favour the right hand reaction, and you'll get more SO3. The triangle H, the delta H, is minus 197 kilojoules per mole, which tells me that that reaction as it stands from left to right is exothermic, because that delta H is a negative number. So we're being asked what will happen to the position of the equilibrium if we decrease the pressure. Well, if we decrease the pressure, that will favour the left-hand reaction with 2 molecules of SO3 changing into 3 molecules of the other 2. That will take up more space. Decreasing the pressure will favour the left-hand reaction, and therefore the equilibrium will shift towards the left. Decreasing the temperature. Now, decreasing the temperature favours the exothermic reaction, and we've already said the exothermic reaction is the one going from left to right, so it's the forwards reaction. Therefore the equilibrium is going to be shifted towards the right. And finally, what would happen if we added more oxygen? Well, if we add more oxygen, then more oxygen will react with SO2 and make more SO3. So it does that to counteract the change. You put in more oxygen and therefore more oxygen will react. And so that will favour the forwards reaction, so the equilibrium is shifted towards the right.